center of mass. What is center of mass? Center of mass is, for any body, center of mass is given by it's a point where whole mass is said to be concentrated. Center of mass is a point where whole mass is said to be concentrated. This is how we define center of mass. For system of discrete particles, for a system of discrete particles, we define center of mass as sigma MIRI, where M1, M2, M3 are the mass of the body. Like we define it as, suppose you have mass M1 over here, say Mi over here, and say Mn over here. So this is R1, this is R2, this is Mi, and this is Mn. Say this is Mn, not this one. This is Mn. So this is R1 vector, all straight line, R2 vector, R3 vector, R1 vector. So center of mass, the position of center of mass is the weighted mean of the position of all the body, where the weights are given by the masses of the body. Then for a system of continuous distribution of mass, we can define for system of continuous distribution of, we define RCM as something like, say, RDM upon integral dm. So if I write RCM as XCMY, YCMJ, and ZCMK, firstly R vector is XI, YJ, and ZK. So this will split into three expression, that is, and YCM will come as upon DM upon DM. So these are the expression of center mass: X coordinate of center mass, Y coordinate of center mass, and Z coordinate of the center mass. See, center mass is useful when you are interested in a study of the whole system of masses. You are not interested in the motion of a single particle, right? So I can write for three-dimensional object, for the object which is in 3 dimension, I can write dm as rho d tau, where d tau can be written as, say, dx dy dz. If the object is 2-dimensional, we can write dm as sigma ds, and ds can be dx dy. For a 1-dimensional object like a rod, we can write dm as sigma dx, right? So this is how the formula can change for different object of different dimensions, right? For object of 3 dimension, I can write it as, let me write it for 3-dimensional object. It can be written as XCM, can be written as triple integral x rho dx dy dz upon dm. YCM can be written as rho dx dy dz. ZCM can be written as I can write it as upon, so this is ZCM. This is ZCM. If rho is constant, I can take it out. I can take rho out and write rho will be taken out over here, and it will be taken out over here, and then they will cancel out. Don't cancel rho putting it inside the integral. You take rho outside and then you cancel out. So this becomes, if rho is constant, then this will be x dy dz upon dx dy dz, and if it is, this will be y dx dy dz upon dx dy dz. This is case when rho is constant. Rho is the volume density of the mass. So volume density. So in order to find out center of mass, we have to carry out these integrals. Alright. Now I'll tell you something about what is the relation between center of mass, the position of center of mass, and the symmetry of an object. We'll discuss with you the relation between how you can predict the coordinates of center of mass by using symmetry of the object. So we have to see here the relation between center of mass and symmetry. Let me rub all this. Now I'll discuss with you the center of mass and its relation with the symmetry. See, usually you have, when we call symmetry, we refer to one of the three symmetry which exist. There are basically three kinds of symmetry which exist in the nature. First one is inversion symmetry. First one is inversion symmetry. So I'll tell you what is inversion symmetry. I'll write a definition. A body is, let me write it a definition. So this is the definition of inversion symmetry. A body or a system is said to have inversion symmetry if there exists a point from where, if we draw any r vector, in whatever environment exists at the tip of r vector, the same environment should prevail at the tip of minus r vector. This point is called inversion center, right? Suppose I draw a sphere like this. So this is a spherical object having the mass rho, mass density rho. Then there exists a point, if I draw any r vector over here, whatever environment prevails at the tip of this r vector. Environment can be mass density, right? Over here it will be mass density. So whatever mass distribution you have over here, the same mass distribution you can find at the tip of minus r vector here. If I draw r vector like this, I don't find any mass over here, so I won't find any mass at the tip of minus r vector. So this particular object has got a inversion symmetry. This particular object has got a inversion symmetry. If suppose we have a spherical object and rho is varying like say kr, in this case also you have inversion symmetry, because if I draw an r vector from this point, whatever mass distribution you have over here, the same mass distribution prevails at the tip of minus r vector. So these 2 points have got the same environment. So even this has got a inversion symmetry, right? If suppose I draw the same sphere and suppose in half of upper half the density is rho and the lower half density is 2 rho. Now this particular mass, this particular body do not have inversion symmetry, because if I draw an r vector, I find the mass of density rho, at minus r I find the mass of density 2 rho. There doesn't exist any point from where if I draw an r vector, whatever environment prevails at the tip of r vector, the same environment is going to prevail at the tip of minus r vector. So this is called, this point is called inversion center. The point is called inversion center. So if a body is having inversion symmetry, then center of mass will lie at the inversion center itself. Center is going to lie at the inversion center. Alright. You can guess the reason why it is so. See, we define axiom as when the body has got an inversion symmetry, rho will be an even function. Rho will be an even function in exponential. You can see over here. Here rho is constant. Here rho is k under root x square plus y square plus z square. Axiom odd function, and the limits will be limits of, say, x is going to be limits of x is minus x square minus z square to plus of a square. So you have this kind of limit. So this function is an odd function, and the limit is of the form minus a to plus a. So what this will become? This will become 0, right? In case of an object having got if object has got an inversion symmetry, then your integrand is an odd function, and the limits are from minus a to plus a. See, a hemisphere does not have inversion symmetry. In that case, your z coordinate will be non-zero. Here, in this case, your x, y, z all are non-zero, right? So it lies at the center. If I take the origin, the inversion center, the center mass will lie at the center itself. So this is inversion symmetry. Now we will look into other kind of symmetry, that is rotational symmetry and reflection symmetry. I hope you understand this. If you have any problem over here, you can just put a question in the forum, right? Now we will look into rotational symmetry. I love all this. Now we will discuss what is rotational symmetry. In rotational symmetry, I write down definition first. So this is rotational symmetry. A system is said to possess rotational symmetry if there exists an axis such that if we draw any r vector from a point on the axis in perpendicular direction, then whatever environment prevails at the tip of r vector, the same environment should prevail at the tip of minus r vector. See, suppose I have this kind of this is a hemisphere. Then if I take this axis, I choose this axis, then you can see if the density is rho, then if we draw any r vector from a point on the axis, then whatever environment prevails at the tip of r vector, the same environment is going to prevail at the tip of minus r vector over here. You can see this. So whatever environment prevails at the tip of r vector over here, same environment is going to prevail at the tip of minus r vector. If we don't have any mass over here, this is, if I take this as the r vector, don't have any mass distribution over here, don't have mass distribution at minus r vector. So this has got a rotational symmetry. This is called axis of. So you can see that the hemisphere do not have inversion symmetry, because if I choose this point, any point, there doesn't exist any point from where I draw any r vector, whatever environment prevails at the tip of r vector, same environment will prevail at the tip of minus r vector. There doesn't exist such a point. So hemisphere do not possess inversion symmetry, whereas hemisphere, but it possesses rotational symmetry. This is the example of rotational symmetry. The example which I take earlier, I told you, if it is rho, if it is 2 rho, say if I have a sphere, upper half has got a density rho and lower half has got a density 2 rho. In this case, this particular object do not possess inversion symmetry, but they do possess rotational symmetry. If I draw a r vector from here, I have the mass of density rho. At minus r also I have the mass of density rho. Here I have the mass of density 2 rho, here I have the mass of density 2 rho. So this particular object lacks inversion symmetry, but it do possess rotational symmetry. Alright. And one more thing, if a body has got an inversion symmetry, it will always have a rotational symmetry, but vice versa is not true. A body has rotational symmetry, it need not have the inversion symmetry. See, inversions, this rotational symmetry sometimes is also called, we call it cylindrical symmetry, so call it, whereas inversion symmetry sometimes is called spherical symmetry. Now we have one more kind of symmetry. Let's see that. That is reflection symmetry. Moving to reflection symmetry, I must clarify that if a body has got a rotational symmetry, then your center of mass will always lie on the axis of symmetry. I forgot to tell you about the center of mass. If a body has got a rotational symmetry, center of mass will be somewhere lying on the axis of symmetry. So you need not find the two corners, you just find one corner, the z axis. If I take this as x, y and z, then you have to find only ZCM. You don't have to find XCM and YCM, which is always 0, since the center of mass will lie on the axis of symmetry. So it helps you. It gives you two corners of center of mass. You just have to find ZCM over here. Now I'll discuss with you reflection symmetry and how center of mass depends on reflection symmetry. So this is reflection symmetry. The system is said to have reflection symmetry if there exists a plane from which, if we draw a r vector from a point on the plane in perpendicular direction, whatever environment prevails at the tip of r vector, the same environment will prevail at the tip of minus r vector. Suppose I have something like this, a cuboid sort of thing. I have a cuboid, say of this kind. Then there exists a plane in between. You can see this plane. This will be a plane from where, if we draw an r vector over here, whatever environment prevails at the tip of r vector, the same environment is prevailing at the tip of r vector, minus r vector. This is rho. So this has got a reflection symmetry. So the center of mass will be somewhere on the plane, somewhere on this plane. So you will get one corner of the center of mass. You have to find out the center of mass on this plane. So you need to find two corners. You got one corner from the symmetry. Right. Now we will take some examples where we will be finding the center of masses. So symmetry consideration will always help you in finding out, in predicting some of the coordinates of the center of mass. Out of three coordinates, you will get 2 or 3, or if it is inversion symmetry, you don't have to do any mathematics. The center of mass will lie on the inversion center itself. If the body has got a rotational symmetry, then you just have to find one coordinate, ZCM. And if it is a reflection symmetry, then you will be able to find one coordinate and just find two other coordinates using mathematics. So this is how we do the questions on.